I don't know.
All right. Today, so last semester we talked a lot about inverse functions. We looked at inverses. One was algebraically. We said, for example, if we have something like y equals 2x plus 1, right? We said, well, to find the inverse of this algebraically, all we did was switch x and y, and then solve the new equation for y, or trig functions. Right? So y equals sine of x, and I flip the x and the y. I take x equals sine of y then. Well, if I want to solve this new equation for y, we need to undo, so I would end up with y equals the inverse sine of x. Okay? Another way that we looked at this was graphically. Okay? We said a function and its inverse are just reflects the line y equals x. So if I take this sine function and I ref this across the line y equals x, it's going to end up looking like this. It's going to be turned on its side. It's going to be the sine function on the y-axis. Another thing that we did last semester was the difference between a function and not a function. So the big one, it has to pass the vertical line test. Obviously, this blue function here does not pass the vertical line test. Right? So it's not a function. The way that we get around that is we restrict what piece we're looking at. Okay, so instead of taking this entire inverse sine curve on the y-axis here, we say that inverse sine is only defined on this piece right here. Okay, if we just take that piece, then it passes the vertical line test. So, on the paper that I just gave you, it shows you that piece of the sine curve and its domain, right? So, we're going to take the domain and the range of just this piece of the sine curve, or the inverse sine curve, I should say. Right? So, our domain, the x values that we're hitting, are just -1 to +1, and then the y values that we take here end up being -π/2 to +π/2.
Why is it just that section? Like, how do they?
That's a good question. I mean, technically, we could have taken, like π/2 to 3π/2. We could have taken that section, and it would have passed the vertical line test as well. But I don't know who decided that this was just the section that we were going to take that passed the vertical line test. But so what? Yeah, just because. I mean, technically, we could take any section like that would be a pi, right? This one we took from -π/2 to π/2, but we could go from π/2 to 3π/2, or 3π/2 to 5π/2. Any of those individual sections would pass the vertical line test. The entire length of the range will be pi.
Okay.
Yes. Yeah. Another way that we'll look at this here in a second is on the unit circle. So every distance of pi, the sine values repeat. Right? It'll be the same for cosine. Every distance of pi, the cosine values end up repeating as well. Right? So we can actually look at something very similar if we do this for cosine. And so turn these off. So cosine of x is a very similar function, right? Cosine of x is actually just sine shifted pi over 2. So if I take this function and reflect it across the line y equals x, we will get this picture. Right? So the piece of this graph that we take is actually here.
Oh, so it's just from one minimum to one max.
Exactly.
Well, it's not an axis, it's a sideways beam.
Right. Yeah. If it's the min and the max of this,
The
just
regular one.
right. Yeah. So this piece then, the x values are still -1 to 1, but the y values now for this piece goes from 0 up to pi. Right. So we say that the range of the piece function that we're looking at is -pi/2 to pi/2. The range of the piece of the inverse cosine function that we're looking at goes from 0 to pi. Right? Those, and hopefully this will make a little more sense when we look at this on the unit circle in a second, but those are things that we just have to memorize. Right? The range for inverse sine is -pi/2 to pi/2. The range for inverse cosine is 0 to pi.
One more question. So, like, if there is a, I can't think what it's called, like a b value, then will it be bigger than pi?
Yes.
Okay, so
Yeah, so if our function was, like y equals, well, we can just look at it on here, I suppose. If we say that our original graph is like y equals 0.5 cosine, something like that, and I were to reflect this across the x-axis, then we could look at
these are kind of stupid questions.
no, not
Like,
stupid
they're,
at
like,
all.
Genuine.
Yeah, so if we then look at this piece here, right, that our domain would still be -1 to 1, but now the range would go from 0 up to 2 pi.
Okay.
Yeah. Yeah, no, that's a really good question.
So it's all correlated.
Yeah.
The same way that it would be.
Yeah, yeah. Any other questions so far? So then we can do the same thing with the rest of our trig functions as well. We'll look at tangent here, but we will skip looking at cosecant and cotangent. Right, so this is the graph of tangent. Right, tangent ends up repeating itself. But if we take one piece of my tangent function, one period, and I reflect that across the line y equals x. Right, so if we do -pi/2 so if I just take that piece, oops. So in Desmos, you can restrict the domain using curly brackets. So I just restricted it to one piece of my tangent function, or one period of my tangent function. If I take this and reflect it across the line y equals x, is this going to work? Yeah. Right. We end up with something that looks like this. Okay. Since my original tangent curve does pass both the vertical and horizontal line test, I can take the entire reflection of the inverse tangent. Okay? So the domain of my inverse tangent here is everything, negative infinity to positive infinity. The range then is just going to be what the domain was for one period of tangent. Right? My range is just going to be between negative pi over 2, positive pi over 2. Okay. We okay with this idea so far? Alright. So let's think about this idea on the unit circle then. Where is my unit circle? So we said that inverse sine, let's talk about inverse sine first, is only defined for angles in between negative pi over 2 and pi over 2. So if I'm thinking about the unit circle, here's 0, negative pi over 2 would be here. Right? And then positive pi over 2 is up here. So inverse sine is defined on this half of the unit circle. Okay? Inverse cosine then, we say, goes from 0 to pi. So red. Inverse cosine then goes from 0 to pi. So what we can do with things like this on the unit circle is evaluate something like this. If I want to evaluate the cosine of the inverse cosine of pi over 4, right? Something like this. So cosine and inverse cosine are inverse operations. So that means they should cancel each other out. But the one thing that we have to check is to make sure that this value is part of the range of our function. So I want to make sure that pi over 4 does fit on my, oops, I guess I color-coded this backwards, didn't I? I did cosine in green. So cosine of inverse cosine of pi over 4. So we want to make sure that pi over 4 is part of this range, okay? It is. So cosine of the inverse cosine just cancels itself out, and we say that this is equal to pi over 4, okay? Similarly, for sine, if I want to find sine of the inverse sine of, negative pi over 3. Well, where is negative pi over 3 on the unit circle? Right? Normally, we just define values from 0 to 2 pi. But where would negative pi over 3 be? Yeah, it would be in the same spot as 5 pi over 3. Right? If I start here and go in this direction, go clockwise, I'll get to 5 pi over 3. Right? This angle would be the same as negative pi over 3. Right? So, what we can say, since my range for inverse sine is negative pi over 2 to pi over 2, this is within that range. Negative pi over 3 is this angle right here. So sine of inverse sine cancels out. We can say this is just equal to negative pi over 3. Okay. What can get a little bit tricky is if we ask for a value that's outside of that range. For example, if I ask for the cosine of the inverse cosine of 7 pi over 6. Okay. So we know that our range for inverse cosine just goes from 0 to pi. 7 pi over 6 is not within that range. However, on the unit circle, a lot of these values end up being, a lot of the x values end up being the same, because we know cosine, we're looking at the x value. So at 7 pi over 6, 5 pi over 6 will have the same x value. Negative 3 pi over 2, negative 3 pi over 2. So I can say that this is actually the same thing as cosine of the inverse cosine of 5 pi over 6. And so we can say that this is equal to 5 pi over 6. Okay, since the cosine values are the same at these points. Similarly, for sine, if I ask for the sine of the inverse sine of 3 pi over 4, well, 3 pi over 4 is not within my negative pi over 2 to pi over 2 range. But if I look at 3 pi over 4 on the unit circle, right, now we're talking about sine. Sine is a y value. So I want to look at the same y value. 3 pi over 4 and 1 pi over 4 have the same y value. Right. So I can say that sine of the inverse sine of 3 pi over 4 would be the same as pi over 4. I could do that for any angle, okay? Because we know that the unit circle is going to keep repeating. Okay? So I could do that for an angle of 100 pi over 4. Right? We would just need to find where that same y value, if we're talking about sine, where that same x value, if we're talking about cosine, occurs. Right? So sine and inverse sine, cosine and inverse cosine. Also tangent, right? We could do the same thing for tangent. Tangent and inverse tangent cancel each other out. We just need to make sure that we're looking at an angle that is within that range. Okay. Questions so far? All right, so let's take a look at using these ideas then to solve some problems. So let me pull up some problems here. Let's start with this one.
Staff and students, please excuse the interruption. Any senior animal science students going on the field trip should report to the annex. Thank you.
Alright. So here's a story problem. So we've got a security camera here. It's going to be installed 20 feet away from the center of a jewelry counter, and the entire length of the counter is 30 feet. We want to figure out what angle, to the nearest degree, should the camera rotate so that it scans the entire counter. Right? So we've got our security camera here, rotating back and forth here to scan the entire counter. Well, what we can do here with a problem like this is split this up into two right triangles. Right? So I can solve for half of the angle that I need, and then use that to calculate the entire angle. So we looked at problems where we were solving for a side a lot in the beginning of this chapter. So here we just want to solve for a missing angle. So we're going to set this up just like we did before, okay? With respect to the angle in question, I want to think about labeling the sides that I know. So with respect to this angle, this 15 feet here, since we're talking about half of the counter, 15 feet would be the opposite side. This 20 feet would be the adjacent side of this right triangle. So if we're thinking back to SOHCAHTOA, if I'm dealing with opposite and adjacent, it's going to be tangent. So even though we're saying that this whole angle is theta, I mean, I guess we can use the right notation and say this would be theta over 2. So we can say tangent of theta over 2, right, since we're just talking about half of the angle we want, equals 15 over 20. Well, now I want to get this angle by itself, so I need to undo tangent. To undo tangent, we're going to take the inverse tangent of both sides. So what we end up with then is theta over 2 equals the inverse tangent of 15 over 20. And then to get our entire angle of theta, I would then need to multiply both sides by 2. So we end up with theta equals 2 times the inverse tangent of 15 over 20. Right? So the question does say that we want our answer in degrees. So when we're typing this into the calculator, we need to make sure our calculator is in degree mode. So if we do inverse tangent, 2 times inverse tangent of 15 over 20, it comes up as 73.73979529. So to the nearest whole degree, that would be 74 degrees. I already did that. Yeah, so just inverse tangent of 15 over 20 is 36.8698. So yeah, I already put in the times 2. We okay with something like that? How about, let's actually find an inverse. Right? So this is going back to the process that we talked about last semester, but we also just mentioned it a little bit ago. To find an inverse function, we switch x and y, solve the new function for y. Right? So f of x is the same thing as y. So this thing like this, x equals 2 sine of y plus 1. So to get y by itself, start by subtracting the 1 over. Divide both sides by 2. And then finally, to get y out of the sine function, I would need to take the inverse sine of both sides. So I'll end up with inverse sine of x minus 1 over 2 equals y. And then just for notation's sake, what we did at the end was we replaced y with the inverse of f of x. So we used this notation. Right? It looks like it's for the negative first power, but we say that that's our notation for the inverse. It's not really negative first power. my original function is 2 sine of x plus 1. Its inverse is the inverse sine of x minus 1 over 2. So if I were to graph both of these functions, they would be reflections of each other across the line y equals x. We okay with something like that? So one more type of problem here. Alright, let's evaluate something like this. Okay, the cosine of the inverse sine of 2 over 3. Okay, so for something like this, okay, we need to draw a picture. What this is saying is we've got some triangle where the sine of a certain angle is 2 over 3. Okay, so if I sketch a right triangle here, what this says is this is the ratio of the opposite side over the hypotenuse. We want to figure out the cosine of the angle for which that's true. So we can say opposite over hypotenuse of this angle is 2 to 3. I want the cosine of this angle then. Well, to get cosine, I need the adjacent side over the hypotenuse. So how do I find the third side of a right triangle here? Pythagorean theorem. So set this up as x squared plus 2 squared equals 3 squared. So we get x squared equals 5. Right. So this side ends up just being the square root of 5. So if I want the cosine then, that would just be square root of 5 over 3. So this whole thing, the cosine of the inverse sine of 2 over 3 is equal to the square root of 5 over 3. Questions on something like that? All right. That's pretty much it.